Right, we're now ready to the next lesson, which is section 1.2 about Boolean algebra and logic gates. Introduction. Finding simpler and cheaper but equivalent realizations of a circuit can reap huge payoffs in reducing the overall cost of the design. Mathematical methods to simplify circuits rely primarily on Boolean algebra. This section provides a basic vocabulary and a brief foundation in Boolean algebra that will enable you to optimize simple circuits and to understand the purpose of algorithms used by software tools to optimize complex circuits involving millions of logic gates. So that's the purpose behind why we try to simplify or reduce the circuit. You need to optimize the circuit to use lesser components, use simpler components. It's because we want to reduce the overall cost of our design without affecting the functionality of the circuit. We try to reduce the cost. Our objectives in this section is to solve algebra problems with binary numbers and use logic gates to perform these functions. And then we will also differentiate FPGA and ASIC. What are these two terms and what is the difference between the two? First, let's define what is a set. This is a collection of objects. So set of elements is a collection of objects usually having a common property. For example, if S is a set and X and Y are certain objects, then the notation X is an element of S. That's how we read it. X epsilon S, X is an element of S, means that X is a member of the set S, and Y with a slash, an epsilon, S means that Y is not an element of S. A equals open bracket 1, 2, 3, 4 and then close bracket or brace. This is a bracket. Alright, if we read it mathematically, it's A is equal to the set containing the elements 1, 2, 3 and 4. Elements of set A are the numbers 1, 2, 3 and 4. Binary operator on a set S of elements is a rule that assigns to each pair of elements from S a unique element from S. Is a rule that assigns to each pair of elements from S a unique element from S. So if we perform a binary operation using any binary operator, we must put into mind that the result of that operation must still be within the set of elements in the set S. For example, we have A and then we have this binary operator. We perform this binary operator in both A and B. The result is C. This symbol is a binary operator if it specifies a rule for finding C from the pair A, B, and also if A, B, and C must be all elements of the same set S. That's the rule for using the binary operator. This operator is not a binary operator if A, B is an element of S and if C is not an element of S. So we can't call this operator a binary operator if the result C is not on the same set as A and B. Let's go to the postulates of mathematical. Let's review the postulates that we have known from algebra or algebra or calculus. We know that there is what we call closure. We have the closure and then associative law, commutative law, identity element, inverse distributive. Let's review them. Closure, for example, a set of natural numbers n is equal to 1, 2, 3, 4, c is closed with respect to the binary operator, plus by the rules of arithmetic addition, since for any a, b, an element of n, there is a unique c. So this is just an example. Closure. Closure is the postulate that explains that the output must be in the same set as the input. That's the closure property. Associative law, it's about the groupings of the elements when we perform the binary operator. So we are using this postulates in Boolean algebra already. If you have this inputs x, y, and z, and then we use this binary operators, it says that if the binary operator is used in this way, first x and y uses the binary operator before we perform the binary operation with z. It says that this is equal to this. So what is changed is the groupings. We first grouped x and y, perform the binary operation, while for the right side of the equation, we first performed the binary operation in y and z before x. That's for the associative law. Still, when x, y, and z are both elements of the same set. Commutative law, it's the order between the elements. Associative is with regards to the groupings. Commutative law is between the ordering of the elements. So x, y, and then for the right side, we have y before x. Excuse me. Identity element. If we have E as identity element, if we perform the binary operation with the input x and the identity element, either in either order, the result is still equal to the input. If we perform the binary operation with the input and the identity element, the result is the input. So it's not affected, the input is not affected. That E is what we call as the identity element. If we can find that value where the input is not affected, it's called the identity element for that certain binary operation. For example, 0 is the identity element of the binary operator plus or addition or plus or, right? Where is it? 0 is the identity element the OR operation. Diba? If we have 0 or x or 0, we're doing Boolean, okay, not the usual arithmetic. This is Boolean operation. Whatever is the input x, this will always result to the same input. Say our input is 1. The result will same as the input, which is 1. If our input is 0, so 0 or to 0, the result is 0, which is same as the input 0. So our identity element for the OR operation is 0. The set of natural numbers has no identity element since 0 is not in the set of natural numbers. Okay. Natural numbers, remember, is 1, 2, 3, and so on. Natural numbers are the counting numbers. So there is no identity element for the natural numbers, set of natural numbers. But if it's the set of real numbers, then we have negative, positive, and even 0. So we already have the identity element. Number 5, inverse. Inverse. When you perform the operation, inverse is when we perform the operation between two inputs and the result is the identity element, then we say that x is the inverse of y, or y is the inverse of x. What's the example? Let's look at this in the next. I know we will encounter it in the next lessons. Distributive law. In distributive law, we will distribute the operation within the groupings. So if we have this binary operator, then there are parentheses. For example, we are performing AND operation between y and z, and then we perform this binary operation between x and the groupings of y and z. If this binary operation or operator follows the distributive law, then we can do this. Then these two sides of the equation are equal. We can distribute the binary operation, so x and y are being performed with the binary operation. Then we AND, since we have AND here, then perform the set binary operation between x and z. So x and y and then x and z. We distributed the binary operation for x and the two elements inside this parenthesis. Field. Field is an algebraic structure. This is a set of elements together with two binary operators, each having properties 1 through 5, and both operators combining to give property 6. The field. So if it has the properties 1 to 5, the closure, the associative, the commutative law, the identity element, and then the inverse, we call it the field. For example, the set of real numbers together with the binary operators OR and AND forms the field of real numbers. So we call it the field of real numbers. So the field is composed of the elements and then the operators. So for the field of real numbers, the elements are the set of real numbers and then the binary operators plus or and and. The binary operator, the symbol plus symbol defines addition. The additive identity is 0. The additive inverse defines subtraction. The binary operator and defines multiplication. The multiplicative identity is 1. So the sum of the same, the plus and the or, and then the multiply and the AND operations. Somewhat similar, but one is applied in Boolean algebra while the other is in arithmetic or the usual algebra. The Boolean algebra, the only distributive law applicable is that of multiplication over addition. Yeah. We distribute A to the groupings of B or C. Boolean algebra, this was developed by George Boole in 1854. Switching algebra, introduced by Claude Shannon in 1938. Is a two-valued Boolean algebra represented the properties of bistable electrical switching circuits. So the switching algebra, we are more of talking about the real hardware, electrical circuits. Instead of the thought of anyway. Huntington postulates. This is with the binary operators or and. It states that first, the structure is closed with respect to the operator and or. Let's just call it plus. The structure is closed with respect to the operator times. It's the closure. It only means that the closure property is applied to the binary operation. To the Boolean algebra. Then number 2, the element 0 is an identity element with respect to plus, that is x or 0 is equal to 0 or x or is equal to x. We've already explained that. Then the element 1 is the identity element 2 times, that is x and 1 is equal to 1 and x is equal to x. Identity element, it makes the input equal to the output when we perform the operation. The structure is commutative with respect to or, that is x or y is equal to y or x. Also x and y is equal to y and x. So we're changing the order, but the output they give the same output. Distributive, the groupings, we distribute the operation. So the operator and is distributive over addition. The operator or is distributive over multiplication. Can you see it? We can distribute and to or, and we can distribute or to and. We should note this one because in usual arithmetic operation, this is not possible. We can't add x to y and yz. But in Boolean algebra, we can distribute this operation. This is equal to x or the quantity y and z is equal to x or y and the quantity x or z. So this is only for Boolean algebra. This is true for Boolean algebra. Take note of that. Number 5. For every element x is an element of the set B, there exists an element x prime, which is an element of B, called the complement of x, such that x or x prime is equal to 1, and x prime is equal to 0. In Boolean algebra, let's explain that. Let's explain it here. X or with its complement is 1, and then x ANDed with its complement as 0. Of course, if we OR the input with its complement, the result will be always equal to 1. If x is 0, we OR it with 1, it will be equal to 1. If x is 1, we OR it with 0, the result will still be equal to 1 because all the possible values are being ORed. So there will always be 1 in the input. And whatever it is, as long as there's 1 in the input, the result of the OR operation will be 1. For the AND operation, whatever is the input, if we complement it, whatever is the input and we AND it with its complement, the result will always be 0 because with the AND operation, it will only be 1 if both of the inputs are 1. But how can both of the inputs be equal to 1 if one of the inputs is its complement? So the result will always be 0. If 1 is the input, its complement will be 0. So the result is 0. If 0 is the input, although the complement is 1, but both are not 1, so the output will still be 0. So that's for number 5. Number 6. Excuse me. There exists at least 2 elements. X, y is an element of B such that x is not equal to y. There exists at least 2 elements. Okay. There's no explanation. I can explain this. Number 6. It means that in my own interpretation, that B is not composed of only one element. Comparing Boolean algebra with arithmetic and ordinary algebra, the field of real numbers, we note the following differences. So we are now trying to differentiate the usual arithmetic or ordinary algebra with Boolean algebra. First, Huntington postulates do not include the associative law. However, this law holds for Boolean algebra and can be derived for both operators from the other postulates. So it's not stated here, the associative law, but it can be proven that it still works for Boolean algebra. Number 2, the distributive law of plus over times, that is x plus y dot z equals x plus y times x plus z, is valid for Boolean algebra but not for ordinary algebra, as what I have said earlier. This is true for Boolean algebra but not for ordinary algebra, where we distribute the operation plus over multiplication. Number 3, Boolean algebra does not have additive or multiplicative inverses, therefore there are no subtraction or division operations. So that's for Boolean algebra. No additive or multiplicative inverses. Postulate number 5 defines an operator called a complement that is not available in ordinary algebra. So if Boolean algebra does not have additive or multiplicative inverses, the ordinary algebra does not have complements. Ordinary algebra deals with the real numbers, which constitute an infinite set of elements. Boolean algebra deals with the as yet undefined set of elements B, but in the two-valued Boolean algebra defined next, and of our interest on our subsequent use of that algebra, B is defined as a set with only two elements, 0 and 1. So it only means that in ordinary algebra we have the set of real numbers, but for Boolean algebra we only have two elements, which is 0 and 1. Let's go to two-valued Boolean algebra. A two-valued Boolean algebra is defined on a set of two elements B, which has the set containing 1 and 0, with rules for the two binary operators plus and times as shown in the following operator. Let's call it dot now. Plus and dot as shown in the following operator tables. The rule for the complement operator is for verification of postulate file. We have already analyzed this one already. We know this one from the truth table, so let's not. Let's go to the basic theorems and properties of Boolean algebra. Duality Principle. It states that every algebraic expression deducible from the postulates of Boolean algebra remains valid if the operators and identity elements are interchanged. That is called the Duality Principle. There's an equivalent operation for plus and that, or and or. So you can familiarize with this one. These are always true. X or 0 is always x, and the equivalent of that by the duality principle, if we replace this plus with the dot, replace the identity element 0 with the 1, the result is equal to x. The same result. It's by postulate 2. Then x plus x prime. Let's not mind this postulates and theorems. We can go back to our previous discussion. Let's focus here. So x plus x prime is equal to 1 by postulate 5. And then x dot x prime is equal to 0. This is x plus x is equal to x. Then x dot x is equal to x. Theorem 1 is the here? Closure. Can't find it. X or with 1, whatever w of x. There's already 1 in the inputs, so the output will always be 1. Then x dot 0, whatever the input. Since it is ended with 0, the output will always be 0. Theorem number 3, it's called involution. If we have the complement of x and we take the complement of that, it will cancel out, so the output will go back to the original x. So the complement of x is equal to x. It's called involution. Commutative, we change the order, so x or y is equal to y or x. Or xy is equal to yx. Associative, we change the order, x or the quantity y or z is equal to the quantity x or y, then or z. And it's dual operation. So x times the quantity y times z is equal to x times y times z. Distributive, distribute the operation of x dot the quantity y or z is equal to x dot y plus x dot z. This, we have already discussed this. X or yz, we distribute the or, so it becomes x or y dot x or z. This is applicable and true for Boolean algebra. The Morgan's theorem, this is one of the very most useful theorems in Boolean algebra. The complement of the quantity x or y is equal to x prime, y prime. So by the Morgan's theorem, we have converted the operation of the OR operation into AND. Replace the OR operation with AND operation, and then we complement each input. For the AND operation, x and y, and then take the complement, that would be equal to, we change the AND to OR, so x, and then we complement each input, so x prime plus, it becomes x prime plus y prime. That is the Morgan's theorem. Absorption, x ORed with xy is equal to x. So the y here did not matter at all. Just equal to x. We can prove that. Let's try proving. X or xy is equal to x. How? X or xy, we distribute by distributive property in Boolean algebra. X or x dot x or y. We know that x or x is equal to x, then we just went back to the original. This is not the right solution. Wait. Okay. By distributive property, can write it down as x times 1 plus y. So x 1 or y is just 1, so it's x. So use the distributive property, which is factored out. Is the important thing. 1 or y is just 1. Then for the other one, x ended with y or x or y is equal to x. X ended with x or y is equal to x. Here we can apply the distributive property. Distributive property. Then by factoring, we'll go back to A, which is factoring. It's x times 1 plus y, and this is 1. So x. That's why it's x, and the quantity of x or y is equal to x. See the book for proving of these theorems. Let's now go to the operator precedence. This is about the priority or ordering of the Boolean operations. So the highest priority is the parenthesis, then the not operation, then the and then the or. Expressions inside parentheses must be evaluated before all other operations. The next operation that holds precedence is the complement, which is the not or complement, and then followed by the and finally the or. Boolean functions. Boolean function described by an algebraic expression consists of binary variables. So we are now in one of the most interesting topics in Boolean functions. This describes an algebraic expression consisting of binary variables, the constants 0 and 1, and the logic operation symbols. For example, f sub 1, which is a Boolean function, is equal to x or y prime z. So our binary variables are x, y, and z. Then the operations are or and then complement and then and. The function f1 is equal to 1 if x is equal to 1. That's how we interpret this one. f1 is equal to 1 if x is equal to 1, or if both y prime and z are equal to 1. f1 is equal to 0 otherwise. That's how we interpret this Boolean function f1. Another example, f2. f2 is equal to x prime y prime z plus x prime y z plus x y prime. If we translate that into logic gates, figure 2.1 shows it. This is for f1. So this is for f1. Let's analyze f1. We created this table, the truth table for f1 and f2. They are two different outputs. Okay, f1 and f2 are two different outputs, but they have the same input, so they're placed. It's okay to place them in the same table. xyz. Then inputs are xyz. So you tabulate in the truth table, you place all the possible input combinations. We have 3 inputs. So for 3 input with possible values of 0 and 1, so 2 possible values. So we have 2 to the power of 3. We have the inputs x, y, and z. So that is 8. 2 times 2 times 2 is 8. There are 8 possible combinations of the inputs x, y, and z. And it starts from 0, 0, 0 up to 1, 1, 1. Starts with 0, 0, 0, then 0, 0, 1, then 0, 1, 0. You increment by 1 each until it reaches to the maximum value, which is 1, 1, 1. So this is the output F1 and F2. You get the output by substituting the value of the input to the Boolean function. For example, let's take this. Input xyz is equal to 0, 1, 1. X is 0, so it will be 0, or let's write it down. Let's try one input. Our input, the input that we have chosen is 0, 1, 1. So x equals 0, y equals 1, z equals 1. What will be the value of f1? Substitute the value 0 or y prime. So 1 prime, and then we end with 1. 0, and what is the complement of 1? That's 0, then 1. But if we end 0 and 1, that's still 0. So 0 or 0 is 0. So we expect the output f1 to be 0 if our input is 0, 1, 1. 0, 1, 1, the output f1 is 0. For f2, you substitute your inputs to f2. It's the same process. And then this is the logic implementation, gate implementation of f1. X is ORed. This is the OR symbol, logic gate symbol for OR. F1 is the OR operation of X and Y prime Z. This is Y prime. We implement prime or complement by using an inverter. So Y prime ended with Z. So let's try simplifying f2. Now we are now capable of simplifying Boolean functions because we have already tackled the theorems and postulates in Boolean algebra. So we should be able to simplify this function f2, Boolean function. F2 is equal to, let's copy x prime y prime z, ORed with x prime y z, ORed with x y prime. Let me try simplifying it. It's been a long time. Where are we going to start simplifying? So let's combine both x. I'll just try because it's been a long time since. So I factored out Just two first. They have common elements, x prime and then z. So what remains inside the parenthesis is y prime and y. This is by you have to check the postulates and theorems. Which one is this? But I know that the value is 1. The value of y prime ORed with y is 1 because all the possible values are there and you are ORing, so there will always be 1. So it becomes x prime z plus x y prime. Can we further simplify this one? Let's try applying the distributive property. So x prime z, let's distribute the OR operation. X prime z ORed with x, and then let's multiply x prime z. Wait. It's not right. Again. X prime z. I will distribute this OR operation to this. So yeah, tama nga. X prime z or y prime. But we can't simplify it that way. So I think the final answer is x prime z plus x y prime. Let's check. Yeah, it's the final answer. The final answer is x prime z plus x y prime. So I'm still right with my answer, x prime z plus x y prime. So what happened? If we draw the logic diagram equivalent for F2, this is the original logic diagram if we did not simplify. So there are how many gates? 1, 2, 3, 4, 5, 6. There are 6 logic gates used with this equation, Boolean function. But after simplifying, we only have 5 logic gates, and each input of the logic gates is 1 or 2 only. Here, we have 3 logic gates having 3 inputs. So this is much more complex compared to the simplified logic diagram, simplified function, Boolean function. As stated here, therefore the two circuits have the same outputs for all possible binary combinations of inputs of the 3 variables. Same output, but each circuit implements the same analytical function, but the one with fewer gates and fewer inputs to gates is preferable because it requires fewer wires and components, and in general there are many equivalent representations of a logic function. Finding the most economic representation of the logic gate is an important design task. Economics, so we are trying to save money. save money, save resources by simplifying the Boolean function, which is a very important design task. Okay, let's go to the examples of algebraic manipulation of Boolean functions. Let's have some more examples. Let's stop here. Let's just continue this in our next video. That will be all for now. Thank you for watching, and please subscribe.